Hello everyone, welcome to our channel, your source for everything related to high-performance network applications. Today we'll talk about high-performance networking and how DPDK helps us reach it. In this video, we'll cover two main parts. First, I will explain the core challenge we face today, exponentially rising performance demands, and the specific bottlenecks within the traditional Linux networking stack that fundamentally limit speed. Second, I will introduce the solution, the Data Plane Development Kit, or DPDK. I'll show you how it solves those problems and walk you through the key engineering principles that make it so incredibly fast. Let's go through this step by step. First, let's understand why we need DPDK and what's happening with network traffic today. First trend, global network traffic is increasing rapidly. Everything, video streaming, cloud services, 5G networks, generates exponentially more data every year. Second trend, network performance requirements are constantly rising. We need not just more bandwidth, but also lower latency and higher throughput for real-time applications. Third trend, expectations for network reliability are higher than ever. Downtime costs millions, so we need 5-9 availability. However, traditional network stacks struggle to keep up with these new demands. They were designed decades ago and hit performance limits at just 1 to 2 million packets per second per core. This gap between growing requirements and limited capabilities creates a real problem. Now, let's examine exactly where this traditional network stack fail. So, what exactly is the problem? The standard Linux network stack is very reliable and flexible for general use. However, for high-performance applications, when packet rates exceed 1 to 2 million packets per second per core, traditional approach becomes a bottleneck. It limits performance and increases latency. Here are the core issues in the traditional Linux networking path. First, interrupt handling overhead. Every incoming packet triggers an interrupt, which stops the CPU, causes a context switch, and breaks the cache. The second issue is double copy overhead. When a packet arrives, it's first received into a kernel buffer and then copied into a user space buffer. Each of these copies wastes valuable CPU cycles and consumes memory bandwidth. Next, kernel user space transition overhead. Every packet goes through kernel system calls. Each system calls force a costly context switch between user and kernel space, burning hundreds of CPU cycles and adding significant latency. Fourth, scheduling and core-to-core synchronization overhead. Threads move between cores. Locks are used to protect shared data, and this creates contention and extra delays. Together, these factors create performance limitations of the Linux network stack. So, the problem is clear. Now, let's see what modern solution we have for these issues. DPDK. Let's explore what DPDK really is and how it overcomes the limitations of traditional networking. DPDK stands for Data Plane Development Kit. It's a set of tools for building high-performance packet processing. The key idea is that DPDK bypasses the kernel's network stack. This means your application processes packets directly in user space, without going through the traditional Linux networking layers. It uses kernel drivers only for initial setup and hardware access. DPDK is not a complete network stack. DPDK provides low-level libraries and drivers. These allow you to build your own fast path for packet processing. DPDK is also portable. It supports different CPU architectures and many types of network interface controllers. Another important point is that DPDK works well with virtualization and can be used inside virtual machines or containers. In practice, DPDK is used whenever we need high-performance network applications that must handle millions of packets per second with very low latency. Now that we know what DPDK is, let's see how exactly it solves the bottlenecks we saw in the Linux stack. We started by talking about the problem of interrupt handling overhead. The solution that DPDK provides for this is its polling model. Instead of reacting to interrupts, DPDK worker threads continuously poll the NIC queues. This removes interrupt and context switch overhead and gives us predictable latency. The second issue was double copy overhead. Normally, packets are copied from kernel to user space. DPDK solved this with a zero-copy model, where packets go directly into user space buffers, eliminating the extra copy and delivering maximum throughput. The third issue we discussed was kernel user space transition overhead. Normally, every packet goes through kernel system calls, which adds significant latency. DPDK uses kernel bypass. The application talks directly to the NIC via the poll mode driver. As a result, there are no system calls and no kernel overhead. Finally, we looked at synchronization and scheduling overhead. Normally, threads migrate between cores. DPDK uses thread affinity. Threads are pinned to specific cores. This prevents thread migration, keeping caches hot, and ensuring predictable performance. The overall result is highly efficient resource utilization, near elimination of software overhead, high packet throughput, and deterministic low latency. To better understand where DPDK operates, we now need to talk about a key architectural concept, the data plane and the control plane. Now, let's focus on the data plane, the DP part in DPDK. Data plane is not just a word in the name. It's a key part of modern network architecture. A key architectural idea in high-performance networking is to separate the control plane and the data plane. The control plane makes decisions while the data plane executes them for every packet. The data plane is responsible for per-packet processing and forwarding. So, what does the data plane actually do? It performs four main actions on every single packet: filtering, packet classification, and match actions processing to decide what happens to a packet; modifying, changing packet headers when needed; balancing, incoming packets across internal processing resources; forwarding, moving packets from one network interface to another based on L2 or L3 forwarding tables. The key characteristics of the data plane are very simple. It works on a per-packet basis, and it's extremely sensitive to latency and throughput. This is exactly the part of the network that DPDK is designed to accelerate. Now, let's look at the control plane, which is the brain of the network. The control plane is responsible for controlling the data plane. It does not forward packets itself. Instead, it prepares all the information that the data plane uses to forward packets quickly. First, it creates the table used by the data plane: routing tables, ARP tables, MAC tables, and so on. Second, it runs network protocols such as OSPF, ERGRP, BGP, ARP, and STP. These protocols exchange information with other devices. Using this information, the control plane learns the network topology and builds the actual forwarding information that the data plane will follow. The key characteristics are very different from the data plane. The control plane handles control logic, not data flow, and it performs strategic computation. It can afford to be a bit slower and more complex because it makes decisions while the data plane just executes them at high speed. Let's look at the DPDK components. Here are the first two core DPDK components. The first is PMDs, poll mode drivers. They implement kernel bypass using user space network drivers. PMDs provides direct access to NICs from user space and use polling of NIC queues instead of interrupts to reduce latency. The second is EAL, the Environment Abstraction Layer. EAL provides the foundational interface between DPDK applications and hardware. It abstracts operating system specifics and hides hardware-dependent details, such as huge pager setup, core topology, and PCI device discovery. Together, PMDs and EAL give us a portable, high-performance way to talk to the NIC directly from user space. The next components are memory management and RIN buffers. DPDK memory management is optimized for packet workloads. It uses huge pages to minimize TLB misses, implements memory pools for fast object allocation and reuse, and manages packet buffers, or MBUFs, for high-speed packet processing. RIN buffers provide high-performance lockless queue mechanism for fast intercore or inter-process communication. They act as simple, efficient communication primitives and optimize for predictable low-latency data exchange between different DPDK threads. Together, these components ensure that data moves quickly between cores and that memory is handled efficiently, which is crucial for a high-performance data plane. Now let's look at the final component, libraries and APIs. These are the tools that you use to build your actual packet processing logic on top of the lower level components we just discussed. Specifically, they offer libraries for packet manipulation, functions to parse, modify, and analyze packet headers. They enable protocol analysis, extract field from Ethernet, IP, TCP, UDP headers quickly. They provide packet classification mechanisms, hash tables, flow tables, ACLs to make fast forwarding decisions. They facilitate efficient packet forwarding, lookup, encapsulation stripping. All these libraries are designed for scalable, low-latency data plane applications. They were optimized for the same performance requirements as PMDs and memory management, millions of packets per second with microsecond latency. In short, EAL and PMDs connect applications to hardware, memory management provides efficient buffers, and libraries give you the intelligence to process the packets. So, today we covered the complete picture of high-performance networking with DPDK. Let's quickly recap the key takeaways. Modern networks face four main bottlenecks in the Linux stack: interrupts, double copying, kernel transitions, and scheduling overhead. DPDK solves each one with a specific technique: polling, zero copy, kernel bypass, and thread affinity, effectively eliminating software overhead. This allows DPDK to accelerate the data plane, the critical path where every packet is processed. And behind the scenes, five core components work together: PMDs, EAL, memory management, RINs, and libraries. This combination of techniques and components is what makes DPDK the industry standard for building high-performance network applications. If you enjoyed this deep dive, please like and subscribe. It helps more people discover the channel. And let me know in the comments what networking topic should we cover next. Thanks for watching, and I'll see you in the next one.